Hi, I'm Cullen Brown.
And I'm Jordan Heaps.
This is our presentation for Computer Science 462 with our project, MusicaLock. So let's take a look at what's actually at work inside the box. Inside, above our false bottom, we have a solenoid, which is actuating on a sliding pin lock to lock and unlock the box. We have buttons and LEDs. You'll see more of them. We're going to have to turn the box around in a moment. You'll see more of them then. We have buttons and LEDs on here for listening and locking and unlocking, and LEDs for confirmation and such. So I'm going to turn around the box so that I can show you the inside, what we're hiding away. Underneath our false bottom, we have a PSOC 5 as our microprocessor that's doing all of the calculations we need for this. We also have a Bluetooth Mate Silver Bluetooth card that we're using to communicate with phone. And we have an electret mic with breakout board for recording audio for conversion. All of this is powered by a 9-volt cell. Alright, so we're going to demo the tone recognition part of our box. We first start by turning it on, and then once it's on, we want to sync the matching Bluetooth app, it's an Android app, to the phone, not the phone, the box. Once we have turned on Bluetooth and paired with the device, we're going to connect to it. And ultimately we're going to be requesting a new key. The key it's going to generate is a 6-note key that all the notes are randomly decided between A4 and G#5. So now you can see we have a new key.
That's just the upward rotate counterclockwise.
Okay.
Should we add... Yeah, I think that's probably enough for the context of the video. We think that's enough, or should we add like a couple more? I was thinking to demo we could just say... This isn't going to do anything for the demo purposes, we could just assume that the thingy is rotated. Actually, it's rotated clockwise. So it's rotated clockwise. Have the inputs for the clockwise rotation.
Here we can take a look at the components that actually make up the musical lock. We have the buttons and the LEDs on the front control panel, the motor and locking mechanism, a little Bluetooth adapter that communicates with the Android phone, and a microphone attached to the central processing unit, the PSOC 5. When the app connects to the Bluetooth module, the user can request a new key. That's the first piece of data that's sent between the phone and the Bluetooth module. The Bluetooth module sends data to the PSOC's UART, which then performs the necessary calculations and sends back information to this Bluetooth chip, which the phone then receives as the new key. Data is picked up from the microphone whenever the user presses the listen button above the blue LED. The data coming from the microphone is a bunch of voltage readings that are sent to the PSOC. PSOC interprets that data and turns them into frequencies. The frequencies are then compared to the existing key, and then data is sent out through the control panel to let us know whether the note was right, a green LED indication, or if the note was wrong, it will be a red LED indication. If all of the notes are played correctly in sequence, the PSOC sends a signal to the locking mechanism to unlock the box. Our motivation for building MusicaLock was that we wanted a simple implementation of many new technologies. We chose Bluetooth, Android development, and audio recognition as 3 areas where we'd like to gain more expertise. And this lockbox was an easy way to put all 3 of those things together.
We had a number of difficulties with this project and learned a great deal from it. First and foremost, I think the largest difficulty we had was the learning curve. Just overall, neither of us really had a strong hardware background, and jumping into technologies like Bluetooth And in my case, jumping into an algorithm like the fast Fourier transform, which I thought I knew and did not, ate up a huge amount of time and caused a lot more work than it might have someone who was a little better prepared. Additionally, we ran into problems of resource constraints on the managing them on the PSOC. As it turns out, the PSOC doesn't have a whole lot of RAM. Our initial implementation of the fast Fourier theorem ate up all of the RAM rather quickly. And that remained a problem until ultimately we ended up getting rid of the fast Fourier theorem altogether and switched to a different algorithm. But we also had issues of power consumption by the parts on the box that needed to be resolved. And lastly, as far as difficulties and issues that caused us to learn a great deal, we were really bad at estimating how long it would take us to do certain parts of this. Overall, combined, the two of us spent about 150 hours over the course of 6 weeks designing, ordering parts for building and programming on the box. And a lot of those, I feel a lot of that time could have been shaved off if we had been a little smarter about estimating how long certain things would take.
For the next generation implementation of our box, there are a few changes that we would make. First of all, we'd like to have better power management. Right now, our box is powered by a 9-volt battery. That battery can run out really fast, and if the box is locked when the battery does run out, there's currently no way to retrieve the battery. In future implementations, we'd have an AC plug on the back where we could charge it whether the box is locked or unlocked. We'd also add multi-octave support and support for more complex waveforms. Right now, it analyzes a simple tone, and we could expand it to include something like full-on music or instrument ensembles. We could also include better noise filtering in our algorithm. We ran into a few problems where the noise level in the room was not what we expected it to be, and that drastically affected our frequency analysis. So with better noise filtering, we have a more reliable opening system.
Overall, I think we learned a great deal about new technologies we had never messed with before, and have a greater appreciation for integrating hardware and software together than we did before this project.